guys, we're going to do lesson 8.1 on vectors. And this actually will probably be the only lesson that we do on vectors given our time constraints here. So part of our assignment is doing the notes, and then we have kind of a fun activity afterwards. So it says we're going to represent and operate with vectors geometrically. And so think making shapes, and then solve vector problems and resolve vectors into the rectangular components. So a scalar indicates the magnitude or size of an object. It doesn't have any direction. So you can see in this first example, it says a boat is traveling at 15 miles per hour. Well, that's fine. That's how fast it's traveling. But is it going this way? Which direction is it going? It doesn't give us any explanation as to where it's going at all. And so since we don't know the direction, it's considered a scalar. A vector describes both magnitude, so some kind of value for the size of it, and direction, so where we're going. In this example, a hiker walking 25 paces due west. So his speed or size, the size is 25 paces. Then we're given his direction so that we know if we're looking at north, south, east, and west, that he's going directly west 25 paces. So he's over here somewhere. So that one's giving us directions. A little information about parts of a vector. A vector has, it should say an initial point, A, which is a tail. So here's our initial point or our tail. And a terminal point, B, so there's our point, and that's considered the tip or the head. And you can see preceding that point there, just at the very end, is our arrow. We can name the vector a few different ways. We could say vector AB. This is the symbol for vector. It's kind of like half of an arrow because those are the endpoints. We could just call it A, vector A, or we could put a little half arrow over it and say vector A that way. Okay, so let's talk about the different ways that we can position a vector or talk about a vector. It says a vector with its initial point at the origin is said to be in standard position. So really think about this like the angles that we did when we were on a unit circle. That when something was in standard position, one of the rays was made with the positive x-axis and the other was to however many degrees we had. And so in this case, our vector is obviously not our angle, but it's right here. It has its initial point at the origin. It has its terminal point B here. And what's happened is it's rotated 35 degrees from the x-axis. So this is a vector in standard position. The length of the segment represents and is proportional to the magnitude of the vector. So the magnitude of A is denoted as this. So what we would usually do if we want to talk about this vector here is we would measure its length. And so in this case, in my picture here, this one is about 4 centimeters. And so if I'm measuring it, I would say this represents the magnitude of A is 4 centimeters. So that's just a little terminology for you, or what the symbols mean. And then the direction is 35 degrees from positive x-axis. Okay, so we're going to look at some examples here. It says represent a vector geometrically. Use a ruler and protractor to draw an arrow diagram for each quantity described. Include a scale on each diagram. So for A, we have, it says A is 20 feet per second at a bearing of north 30 degrees east. And so, you know, what does that mean? A bearing north 30 degrees east. And so, because I'm using direction here, instead of having a normal X and Y axis, I'm going to go north, south, east, west. And it says, first of all, north 30 degrees east. So from the north, I'm going to turn 30 degrees towards the east. So north to east. So I'm going to just kind of draw roughly how much that is. So if I were doing 30 degrees, we would say, we would know roughly where that is. That's right in here, I would say, is that's a 30 degrees north 30 degrees east. And then it says 20 feet per second. So I'm going to give a scale for this, and I'm going to say I'm going to let 1 centimeter equal 10 feet. So if I want to represent 20 feet, obviously that's going to be 2 centimeters is 20 feet. So I would get my ruler out, and I would mark along that line where 2 centimeters is. And that's actually the end of my vector. Okay, this is the initial point here, and here's my terminal point. And that's it. That's 20 feet per second. And this is the scale of my diagram. And you can I just used something that was really easy to work with. You could do anything that you wanted to, really. Okay, the next one, B, it says 75 pounds of force at 140 degrees to the horizontal. So this is not north, south, east, and west. This is just a normal X and Y axis where the horizontal is your horizontal axis. So we have X and Y, and so I would want to measure from the horizontal. So it says 140 degrees to the horizontal. So one side is the horizontal axis and the other side is the vector itself. So I'm going to go around. This is 90 and another 50. That's going to be about probably right in here. I don't want to completely draw the vector. I'm just going to do it this way. Okay, but I've gone 140 degrees from the horizontal meaning the horizontal axis. And now, how do I represent 75 pounds of force? Here's what I'm going to do. 75 pounds, and this is how I would work it out. I would say, well, it's easily divisible by 3, and 3 centimeters is something that I could measure easily. You might have a different scale. It does not have to be the same. So I'm going to let 1 centimeter equal 25 pounds of force. So 3 centimeters would have to be 75 pounds. Okay, so there's my scale that I'm going to use. And then I'm just going to mark off 3 centimeters, and that's that's the magnitude of my vector. So it ends up being about right there. And so my vector is right here. It's the black part. And so maybe you're pulling something along here, going from this direction at an angle with the horizon. And C, 30 miles per hour at a bearing of 60 degrees west of south. Okay, 60 degrees west of south. So we want to talk about what that looks like. Obviously, we're doing directions again. So we want north, south, east, west. If it doesn't specifically talk about north, south, east, or west, then it's going to be an XY axis. The other key word here is bearing, and that's a navigational term, which would also be north, south, east, and west. All right, so we've got 60 degrees west of south. So that means we're starting at the south, and we're going to go west of there. So we want to go this direction. So from the south end, this being our initial point, we want to go 60 degrees. So I'm going to guess it's about right there. I might be off just a little bit, but you could always measure that. Okay, I'm just going to say that it's 60 degrees. And then I want 30 miles, and you can probably guess what I'm going to do. I'm going to say, let's let 1 centimeter equal 10 miles. Okay. So 3 centimeters would be 30 miles. I could have done let 1 centimeter be 15 miles. And so I would have represented it with 2 centimeters. You can do lots of things with this. You just have to make sure that you give your scale so that we know what to reference. And again, I can do 3 centimeters here. And that will be where my vector is. So this would be, let's say I'm in a boat. Okay, now we don't do too much of a boat. Maybe we're out in the woods or something even. And we're traveling on, I don't know, an ATV or kind of a small all-terrain vehicle. Maybe we're just in a Jeep out in the woods somewhere. And so we're navigating and we're going 60 degrees west of south. And then we're going in this, continuing in that direction, 30 miles an hour. So you get a little bit of an idea of what vectors are and what they represent. This is just some extra terminology. We've got parallel vectors. That just literally means that they are parallel to each other. It says they're going in the same or opposite direction, but not necessarily have the same magnitude. So we have 2 here, vectors that are going in the same direction. Their magnitudes are different because their lengths are different, but I have parallel line symbols here. So those are parallel vectors. Equivalent vectors are the same magnitude and direction, so really identical. So these guys are parallel to each other because they're going in the same direction, and then they're the same length, same magnitude. And opposite vectors have the same magnitude, so same length, but they're just going in completely different directions. It says vector A is written as negative A. So let's say this is vector A. Since this is going in the opposite direction, this is negative A.